So when we write things in the void notation, we also have to rearrange the strain displacement relations so as to be compatible with this notation. So this is my tensorial equation. We know this. And now I have ordered the strains in this way. So epsilon 1 is epsilon xx, 2 yy, 3 zz, 4 is 2 epsilon xy, then 2 epsilon yz, 2 epsilon zx. This is my ordering. And from the strain displacement relation, the first one is related to the first component of displacement, second, and this you have the 2 here cancels with the half here, and then you will have del ux del y plus del uy del x, and these will be del uy del z plus del uy del z plus del uz del y, and then del uz del x plus del ux del z. So these would be the 6 components in terms of the displacements. So this is what I have written here, the 6 components. It can further be written, and we will often write this in terms of an operator matrix, which we call this fancy L, times a vector which constitutes of the 3 components of the displacement. So ux, uy, uz as a vector times this operator matrix which has del x here. So this multiplies with this to give you del ux del x, which is equal to epsilon xx. We have seen that. Similarly, epsilon yy is del uy del y. So this row multiplies with this column to give you that. And then similarly here. And then for the shear strains, we have 2 entries, del y in the first column, del x in the second column. That gives you del ux del y plus del uy del x, which is what 2 epsilon xy is, and so on. So this is the form of the strain displacement relationship that we will use, and symbolically we will write it in this manner, where it is understood now that this epsilon is now a vector, u is now a vector, and these are all in Voigt notation corresponding to the ordering that I have chosen for stresses as well as strains. Now here is the situation under the most general case. This is just again a recapitulation of the recapitulation that I did. So you have this 3-dimensional body occupying a volume V, and then there's part of the body which we are going to call delta Vt, on which tractions might be specified, and these tractions are denoted by bars. There may also be concentrated forces specified, but concentrated forces are actually a special case of the tractions, but we have just shown them both. So tractions may be specified, concentrated forces, which are special cases of tractions, that may be specified. And then there is another part of the boundary which we will call del Vu, on which displacements are specified. The displacements are specified. So this is the nature of the boundary condition. On part of the boundary delta Vt, you have the tractions specified, and don't forget that the tractions are related through the Cauchy relations to the stresses right next to their point of application. So if this traction is known, the stresses right at the boundary have to obey this relation. So Tx bar, Tx bar, Ty bar, and Tz bar are the attractions. These are specified. So Tx bar must obey this, where Nx, Ny, and Z are components of the outward normal at that point. Ty bar has to obey this. Tz bar has to obey this. What I have written here is, as you can understand, Ti bar equal to sigma ij, and j is what I have written here in matrix form. So on delta Vu, you will have u equal to u bar, again another sort of boundary condition. And the important thing to note is that del Vt, del Vu together will give you the entire boundary, and they do not intersect with each other, which means that at every point on the boundary, you have to either specify the tractions or specify the displacements, but at no point on the boundary can you specify both. That is the long and short of it. At each point on in the volume of the material, of course, the equilibrium equation must be satisfied, sigma ij comma j plus bi equal to 0. The displacement and strains must be connected through the strain displacement relationships, and the stress and the strain must be connected to through the constitutive equation, which in our case is the are the equations of linear elasticity. So this gives you 15 equations in the 15 unknowns. This is a closed system which can be solved with these boundary conditions in the ideal case. However, we will not get into this ideal case with all, in all its glory right now, but we will look at some of the simplified situations that can arise and that can quickly be handled in finite elements. So the first one, let's do this problem first. So so what we are going to do here is, and this is an important exercise that we have to do, because in finite elements we need to specify this information about the boundary conditions and the governing equations very precisely to the code, so that it can do what you want it to do. So we will take up a few examples where we will try to define the boundary condition in this very formal way. Now, look at this problem. There's a beam, a rectangular beam, and you have a distributed load applied here, and XY axis is defined. So, first task is to try and figure out what is delta V, delta Vt, and which part is delta Vu. Now, in this problem, what we can see is the displacements are held at 0 on this part. So this part is my delta Vu. And the rest of the boundary, the upper surface, this edge, there are no displacements specified, but on part of this, tractions are specified to be 0. So these are traction-free boundaries, and the entire boundary, entire rest of the boundary constitutes, so this entire boundary constitutes del Vt. Now, so at x equal to 0, everywhere at x equal to 0, here you have ux bar, uy bar specified as 0. At x equal to L, the outward normal is 0, outward normal is 1, 0, 0, and the tractions are 0. So the traction vector is 0, 0, 0, and you have sigma xx nx, which is 1, plus sigma xy ny, which is 0, plus sigma xz nz, which is also 0. Then you have sigma xy nx, which is sigma xy because nx is 1, plus sigma yy ny yz, and similarly you have xz here plus 0, 0. This is the application of Cauchy relation to this surface, and here you can immediately see that sigma xx has to be equal to 0, sigma xy has to be equal to 0, sigma xz has to be also equal to 0. So on x equal to L, Tx bar is equal to 0, implying that sigma xx, sigma xy, sigma xz all are 0 on this surface. Again, on the lower surface, this normal is 0, minus 1, 0. And the traction vector is again 0, 0, 0. It's a traction free surface, and this will imply again that this is equal to sigma xy, sigma yy, sigma zy. So these three components of stress have to be equal to 0 on the lower surface because the normal is in the negative y direction. Similarly, on this part, half of the upper surface, the normal is in the positive y direction. This is traction free, and therefore, uh, again, sigma xy, sigma yy, and sigma zy are 0 on the top part. What about this part? On this part, the traction is not 0. That's not a traction free surface. You have 0 minus wy, 0 is the traction. The normal is in the y direction, positive y direction. So on this side, I will have sigma xy ny, that which is 1, sigma yy ny, which is 1, sigma yz ny is equal to 1, which will imply that sigma xy is 0 there, but sigma yy is equal to minus w, and sigma yz is 0. So that is what has been defined for the surface x lying between L by 2 to L, L by 2 to L at y equal to h. That surface has this boundary condition where sigma yy is equal to minus w. Okay, all other stresses are 0 on these surfaces. So this is how you define the boundary conditions correctly. You need to do this in order to model something in finite elements. Let's take another case where you have a plate with a hole, and at so here there is no del vu. So del vu is a null set. There is no portion of the boundary on which displacements are specified. So the entire boundary is equal to del vt. Now the hole is traction free, but let us look at these surfaces first. So on these surfaces, the normal is again 0, 1, 0, and the stress and the traction is 0, sigma naught, 0. And since the normal is 0, 1, 0, apply the Cauchy relation, it will mean that sigma xy into 1, here sigma yy into 1, sigma yz into 1. This is the Cauchy relation, which will imply sigma yy is equal to sigma naught, sigma xy, sigma yz are equal to 0 on this face. On this face. On the lower face, again you will have the same thing. So your this is negative because this is pointing in the negative y direction, but the normal also is 0, minus 1, 0. So you will have sigma xy minus sigma xy, you will have minus sigma yy and minus sigma yz, which will tell you again that sigma yy is equal to sigma naught, sigma xy yz are equal to 0. So at a point right next to this, you must have sigma yy equal to sigma 0. At a point right next to this, you must have sigma yy equal to sigma 0. Similarly, on this surface, the normal is 1, 0, 0, and it's a traction free surface, which will mean sigma xx, sigma xy, sigma xz are equal to 0. Similarly, here the same things will apply. Xx, xy, and xz are 0. Okay, now we come to the surface of the hole, this surface. Since this is a circular surface, it would be easier. You can specify the boundary condition in terms of Cartesian coordinate system, but it would be easier to specify it in terms of the r theta coordinate system. So let's take r here and theta here to describe this boundary condition, and then you can immediately see that on r equal to a, which is the surface of this hole, the normal is in the minus er direction. So er is the unit vector along r, and the normal is along the minus er direction. other components of the normal. So therefore, you can write the normal as 1 times ER, and E theta and Ez components of the normal are 0. And therefore, if you now write the Cauchy relation for say TR, you have sigma RR NR plus sigma R theta N theta plus sigma R Z N Z, out of which this is 0, this is 0, and this is 1. So it immediately shows, since TR is 1, this is a traction free, TR is 0, since this is a traction free surface, it immediately implies that sigma RR is equal to 0. Okay, so from T theta and Tz, you will infer that sigma R theta, sigma R Z are also equal to 0. Okay, so on this surface, sigma RR, sigma R theta, and sigma RZ are 0, and on these surfaces, this is the situation. On these surfaces, this is the situation. Okay, now a slight twist to this problem. Um, Instead of having a hole, you have a rigid particle sitting inside this hole, and it's strongly bonded to the plate. So now the rigid particle will not let this boundary move when it deforms. So it is basically like specifying, you can remove the rigid particle and you can specify displacement boundary conditions here, and this would be part of your del VU, and the rest of the boundary would be del VT. So on this boundary, since this is a rigid particle, all other boundary conditions would be similar to the boundary conditions on this face, and on this face would be similar to what we had in the previous problem. But on this boundary at r equal to a, you will have u equal to 0, implying that both ur and u theta, radial and tangential displacements, so displacements in this direction and this direction, are both equal to 0. You can of course do this in terms of ux and uy, but it would be easier to do it in Cartesian polar. So this is a problem where you cannot impose the boundary conditions in quite the way that we have learned so far. These are two beams which are just resting on each other over this region A. Obviously, this is part of your del VU. This is part of your del VU, and the rest is part of del VT, except this part, where when you apply this load, this beam and this beam, let us assume that they will remain in contact, but it's not necessary that they remain in contact over the entire region A. So if we take the initial part of this beam, so I'm drawing only this part, and then initial part of the lower beam, let us assume that the lower surface of the upper beam is this, and the upper surface of the lower beam is this, and they are in contact at this point. So uh, the condition that they remain in contact would be that uy2 has always got to be higher than uy1 over this entire region um, from here to here. So for this region, we must have an inequality constraint on the displacements, that uy2 is always greater than uy1. We cannot have an equality constraint, and this inequality constraint this is kind of a contact constraint which cannot be imposed in a straightforward manner on the finite element equations. So for the time being, we'll avoid these kinds of problems, but there are ways to deal with it. If time permits, again, we will see how these are done.